We will discuss dead stellar objects in this video, which are all celestial objects that are left over from the final stages of a star's life. These objects include planetary nebulae, white dwarfs, supernova remnants, neutron stars, pulsars, magnetars, and black holes. However, we must first briefly discuss how stars are created and how they develop in order to comprehend how these celestial things are made. All stars are created in the densest regions of the huge molecular clouds that make up the interstellar medium. These clouds are primarily made of hydrogen, with traces of heavier chemical elements and 23 to 28% helium. Because the hydrogen that makes up these nebulae is ionized by the ultraviolet radiation that the stars that form inside of them emit, they are also known as HII regions. Remember that the notation HII indicates hydrogen ionized once. One of these molecular clouds will exhibit gravitational instability and start to contract due to its own gravitational pull if a supernova explosion or a collision between galaxies crosses it, and inside, in the densest regions of the nebula, a protostar will start to form, a celestial body that emits radiation precisely because of the gravitational contraction. The mass of the star will now determine how the star will evolve in the future. A celestial body slightly larger than Jupiter, in which the only two sources of energy are gravitational contraction and the fusion reactions of lithium and deuterium, an isotope of hydrogen whose nucleus is composed of a proton and a neutron, becomes a brown dwarf if its mass is less than 8% of that of the Sun. The nucleus's very moderate temperatures, a few thousand degrees at most, prohibit the development of the thermonuclear fusion events seen in the most massive stars. Under the limit of 13 Jupiter masses, we no longer speak of brown dwarfs, but rather of gas giant planets, and above 65 Jupiter masses, lithium fusion is also possible. Brown dwarfs typically have masses between 13 and 65 times the mass of the planet Jupiter, and in this mass range the fusion of deuterium occurs. Brown dwarfs cool down over time and lose brightness because of their extremely low masses. Brown dwarfs cannot be seen with the human eye due to their extremely low brightness. The protostar moves on to the main sequence phase, a stable stage during which hydrogen is melted in thermonuclear processes, which are powered by the star's mass if it is greater than 8% of the Sun's mass. The temperatures in the stellar nuclei are of the order of tens of millions of degrees during this phase, and the stars are in a state of hydrostatic equilibrium where the radiation pressure produced by the thermonuclear reactions, which tends to make the star expand, counterbalances the force of gravity, which tends to make the star contract. Even the type of thermonuclear reactions varies depending on the mass of the star. The carbon cycle predominates in stars with a mass higher than 1.5 times that of the Sun, while stars with a mass less than 1.5 times that of the Sun undergo hydrogen fusion through the proton-proton chain. Because of the differing masses of the stars, the main sequence phase lasts for varying lengths of time. For example, the Pleiades are an example of a big star that stays in the main sequence for a few tens of millions of years. Instead, smaller stars like the Sun and others stay in the main sequence for billions of years because they burn hydrogen more slowly. The main sequence phase of our Sun is thought to last for roughly 10 billion years in total. Our star is roughly in the middle of this phase right now, but consider that red dwarfs, which are even smaller than the Sun, might stay in the main sequence for much longer than the universe's current age of almost 14 billion years. Isn't that unbelievable? How do you feel? Please leave a remark with it. Consider loading two vehicles, a large truck and a little car, each with 50 gallons of gasoline to get an idea. Which of the two cars will use up the fuel first? The truck obviously needs a larger engine to function because it is larger and more powerful than a little automobile. What transpires if a star's core runs out of hydrogen? Since the radiation pressure produced by the combustion of hydrogen fails, the star is no longer in a state of hydrostatic equilibrium and will consequently begin to contract as it departs the main sequence phase. The star's outermost layers will then impose a certain amount of pressure on its innermost layers and core. As a result of the increased pressure on the star's core, the core temperature will rise to values of the order of 100 million degrees, triggering further thermonuclear reactions. This time, however, helium will burn instead of hydrogen, resulting in the production of carbon and some oxygen. In the case of the Sun, it is thought that it will become a red giant in roughly 5 billion years. If the Sun of this extremely distant future were in the place of the current Sun, its outer gaseous envelopes would come to lick the orbit of Venus. What do you think could happen? Even the Earth would probably not fare well. Please leave a remark with it. Depending on their mass, stars evolve in different ways following the red giant phase. The outermost layers of the red giant will slowly spread into space, almost like a swollen soap bubble, and form a planetary nebula in the case of less massive stars, like our Sun. It is crucial to note that planetary nebulae have nothing to do with planets. It appears that William Herschel first suggested this name sometime around 1780 because the expanding gas bubbles he saw through his telescope plainly reminded him of planetary systems in the early stages of development. The planetary nebulae appear spherical when viewed via a telescope, and some of them resemble smoke rings or donuts in appearance. A 20 centimeters telescope can be used to view M27, a planetary nebula, in the direction of the constellation of Vulpecula, and M57 in the direction of the constellation of Lyra. And what happens to the middle region, or the rest, of the star? When a white dwarf forms, an extremely dense and compact object, consider that it is around the same size as our planet but has a mass that is only 1.4 times that of the Sun. The Chandrasekhar limit, named after the astrophysicist Subrahmanyan Chandrasekhar, who came up with the figure of 1.4 solar masses, denotes the maximum mass that may be ascribed to a white dwarf. White dwarfs have ridiculous densities, roughly in the range of 183,000 G/cm3. In reality, a cube with sides that are each 1 centimeter thick would weigh over 2 tons, 1830 kilograms. If this cube dropped on your foot, what would happen to you? Please leave a remark with it. White dwarfs cannot be viewed with the naked eye due to their low luminosity, but the brightest ones can be observed with Newtonian telescopes with at least a 20 centimeters aperture. Nearly 8 light-years away from Earth and a companion to the more well-known star Sirius, Sirius B is one of the most well-known white dwarfs. What transpires to the largest stars instead? They also go through the red giant phase, but because of their greater mass, the helium in the nucleus burns considerably more quickly. When the helium runs out, the radiation pressure caused by the helium's combustion causes the star to violently collapse in on itself from the force of gravity. The star's core experiences a sudden rise in temperature as a result, and additional thermonuclear reactions ensue, producing chemical elements heavier than carbon and oxygen. The star's outer envelope also experiences a very rapid rise in temperature, which causes it to explode violently in space, resulting in a supernova explosion and the creation of a supernova remnant. The Crab Nebula M1, which is around 6,300 light-years away from Earth and was created by a supernova explosion that was detected by the Chinese in 1054 and described as a host star, is one renowned example of a supernova remnant that can also be seen with an amateur telescope. Chinese documents claim that it peaked at magnitude -6, making it around 4 times brighter than Venus. Petroglyphs that have been discovered in Arizona's Navajo Canyon and White Mesa, as well as New Mexico's Chaco Canyon National Park, appear to be Anasazi Indian representations of the occasion. When Halley's Comet was due to make its initial return in 1758, French astronomer Charles Messier noticed M1. The breathtaking Swan Veil complex is a well-known supernova remnant that astrophotographers adore. What's left of the nucleus also transforms into a neutron star, which is an extremely dense and compact entity rather than a white dwarf. These objects contain degenerate matter, which is so compacted that weak interactions between protons and electrons cause them to combine to create neutrons. These celestial bodies typically have masses between 1.4 and 3 solar masses, which is larger than Chandrasekhar's limit, and a diameter of about 10 kilometers. If the density of a white dwarf didn't already astound you, the density of a neutron star with 3 solar masses is even more astounding at 1015 G/cm3. In other words, it exceeds the previous one by roughly 800 million times. It is unquestionably fortunate that a neutron star matter cube does not fall on your head. There are various different kinds of neutron stars, but the following are the most significant. Pulsars. These neutron stars revolve extremely swiftly on themselves and emit 2 radio wave beams from their poles, resembling a lighthouse at a port. In 1 second, the fastest pulsars even spin 1,000 times around themselves. Astronomer Jocelyn Bell made the first pulsar discoveries in 1967. If you have any amateur radio acquaintances, you can ask them to let you listen to the sound of pulsars, as they are not visible to the unaided eye, but rather by their emission in the radio band. The magnetic field of a magnetar is extremely powerful, between 10 and 15 Gauss, billions of times stronger than the magnetic field of the Earth. Magnetars are similar to pulsars, which is instead around 1 Gauss. Magnetars also release gentle gamma rays as a result of their extremely strong magnetic fields. What happens if the star's starting mass is higher than 3 solar masses? After the supernova explosion, the core of the object collapses into a black hole instead of a neutron star, creating a celestial body whose gravitational pull is so strong that not even light can escape. Because a black hole does not emit light, it is invisible to human eyes. A black hole is a region of spacetime with an extremely great curvature from a relativistic perspective. Drop a line below and let us know what you think, if you haven't already.